right?
Yeah.
Yes, we are here to talk about Gluster, and we're here to be able to talk about not only what we're doing right now, but also the future of Gluster. Gluster has been a project in development for 10 years, which, again, we all know, but I'm not asking for, I think, where the next 10 years is. I want to talk about where the next 10 months goes. Have you seen all the schedule? You know that we're going to be talking about a lot of different pieces in here. We'll be going through like some of our internal workings, the pieces that are coming up. DHT2 comes up today in a pretty direct fashion. We'll be also talking about the overall ecosystem, and that's supposed to be an ecosystem down there, but all of the slides have actually been, if you sent me your slides, they have been posted over on SlideShare, and they are getting tweeted out at the appropriate time of day, so you don't have to worry about it. People are going to be watching. People are going to be looking for this. We are also going to be recording all of these talks and putting them up on our community YouTube and seeing what kind of feedback we get, what people are interested in, and where we should go from here. Questions? Housekeeping notes. You saw the email that I put out saying it would be great if you could not have your laptops open in the room. Now that you're here, I think you can maybe see why that is. There's not much power, there's not much space, and I really want to make sure that we're kind of focused here. We do have open spaces in the afternoon. Okay, we've talked about project process. This is going to be something that Nigel and the rest of us are going to be kind of talking about how basically we create the things that we're doing. And the questions that some people have had about open spaces and birds of a feather. Here's what I think we can do. We've got 2 slots available in the afternoon for open spaces, birds of a feather. On the back table over there, and we'll do this at lunch, we've got painter's tape to be able to tape things up that you want to be able to talk about, paper to write on, Sharpies. There's also going to be pens running around. If there's something that you really want to be able to lead a discussion about, let's work on choosing 3 for each slot. Again, we're going to get a little bit of time to be able to sort this out, but as things come to you, feel free to go to the back of the room and put something up, and then we'll work out from there. It'll only take us a few minutes, but it's really vote with your feet wherever you want to go. Other pieces coming up in here. Reception, downstairs at 5:30 at the LA Cafe. This is a private reception for just us. This isn't like the whole gigantic LinuxCon. This is just us downstairs in the LA Cafe. It's the big space where breakfast for the hotel was when you walked past it. Okay, good. Everyone knows where that is. I'm sure we'll figure it out. We also have a collection of boxes of fun swag that has come in. We'll put that out at the end of the day so it's not like, you know, kind of running around and trying to make sure that we found everything. But backpacks, coffee cups, notebooks, pens, and my favorite, colored pencils. So Gluster proper, here's some things that are coming up. Right now, Outreachy is one of the things we're focusing on. We'll be doing some work with documentation and some work around performance testing, and Shyam and I are the people to talk to about if you want to be involved in that. DevConf. DevConf is coming up. You saw that I put out the call for proposals. They've moved it a bit, so this year DevConf is January, and then FOSDEM, I found out yesterday that we actually do have an open source storage dev room. So, watch for that. Okay, that's pretty much it from me. Questions? You guys are not awake yet. Okay, that's fine. All right, get some more coffee, and we are actually running right on time. So, next up. No? Okay. You don't want to talk? Yeah. Really? No questions? Everyone cool?
Yeah.
Cool. All right, that works.
So it's not connected to
Oh,
projector.
did you lose things? Can you help?
Yeah, so it's not connected to projector, I think. Is it?
Oh.
Let me start it.
Okay, so then I'll fix it later. But there.
Okay.
Any more
I have
assistance?
this one.
Oh. Alright, moment of technical difficulty. Get a cup of coffee. Talk amongst yourselves.
Yeah. Talking of technical difficulty, did no one really ask about the Wi-Fi password yet?
So it's on the, well, okay. The Intercontinental will let you in to be able to get things. Oh, yeah, one note. Even though, like, you know, laptops, like, you know, if you need to go out and do something, totally understandable. But if you have something that you want to be able to say on social media, absolutely. I'm going to be watching for it and basically pushing this out through the Gluster official account. If there's something you're excited about, if there's something you're learning, if you really just want to be able to share, go for it. Better? Okay. Well,
Oh,
you have two then. Okay,
Yeah.
kill the other one. Open source, it works sometimes.
there's the other one. Okay,
Here, kill the other one.
that's kill.
No, the, yeah, that one. Well. And then we quit out of everything. No.
Let me close this one too.
No.
Yeah.
Yeah, exactly. That one. It's kind of like Twitch, but for slides.
How do I start over?
Okay. Okay.
How do I start over?
How about? Can you start over? Yeah. Other one.
Yeah?
Can you tap on F11?
1 minute. Let me get to the start of the presentation. Okay.
All right. Pretty good. Okay.
F11. 11.
Okay. For some reason F11 is actually moving the present slides.
No, you should not play.
Okay.
Don't play.
Don't play.
Don't play it?
Just play 11.
It's door 24.
11. Play button. Just 11.
Oh,
Don't click on it.
this is not the one?
That's not.
Okay. Okay, we'll start off with this. I think it's fine. Yeah, so okay. Cool. Okay, so the presentation is structured into two sections. The first section speaks about the pain points, and the data has been over there in terms of the bugzillas, the customer escalations, the user mails, and all those things. So I just summed it up the points over here, and the second section basically speaks about yes, there is all this complexity. Probably what are the benefits out of those complexity? Okay, so one of the main pain points is basically the replicated directory structure across all the subvolumes of a DHT, and it's not trivial to maintain that mirroring of the mirroring of the directory structure. So one of the common issues we faced is basically the lack of transaction. DHT till quite recently didn't have transactions to maintain the atomicity of operations, directory operations like an mkdir, rmdir, or renamedir. That resulted in a lot of inconsistencies. So basically, when you say directory in DHT, basically we are concerned about two things basically. The directory structure and the layout, basically the layout which says about how the files are distributed across the subvolumes for this directory. So the lack of atomicity resulted in the layouts going bad and the directory structure also going bad. When I say the directory structure going bad, it can mean two things basically. One is the ID, the internal GFID, which represents any file object or directory object within the file system, should remain the same for the directory across all the subvolumes. So because it's the same directory, if the GFIDs are different across subvolumes for the same directory, we'll not be able to map it's the same directory. So so the GFIDs for the same path, basically having the same path on different subvolumes having different GFIDs can result in very difficult issues. So if you are a user using on the mount point, you could see weird behavior. If you do an ls, you could see all question marks for the files. those kind of issues basically. The mapping between the name and the GFID, they can go bad to sum it up actually. If you and one of the common errors you might have seen while because of this issue is E not empty, and ls giving out the question marks. So we have been working on this for quite some time actually, to be honest, and we have some solutions which is basically a locking to introduce the atomicity, but the current locking scheme is kind of O of n. So basically it requires in the normal directory operations like rmdir or rename_dir, it requires acquiring lock on all the subvolumes, which is bad for scalability anyways. The current things we are working on is a more refined locking algorithm which doesn't suffer with the problem of ON. So instead it is the cost is constant, which is basically O of 1. We do have increased latency, but that increased latency won't get worsened as you add more subvolumes to the volume basically. And a sub problem in that is basically a crash consistency. So the atomicity can be viewed across space, basically when an operation is happening at the same time, whether the atomicity is maintained when the operation is having on multiple subvolumes, or the atomicity can also be viewed across the time, which is basically the crash consistency comes into picture. So all the snapshotting, the client crashing while an mkdir or rmdir is in progress or rename_dir is in progress, they can also lead to similar symptoms, similar issues with similar symptoms. So that is also a challenge, and the locking algorithms we are speaking about, they don't really address this crash consistency, so that requires more work over there. The other subpoint with the challenge with maintaining the replication directory structure on the subvolumes is basically you need the path information to heal the directory structure. When do you need the create back this directory structure? You need to create this directory structure. For example, you add a brick. So a new brick basically doesn't have the directory structure. However, the application has already been in the middle of an operation. Basically, the add brick and whatever the application operations the application is performing, they can be independent operations. They are independent and synchronous. So a directory, an application might have already cd'd into a directory, and you might add a brick. The user might add a brick at that time. However, the application should continue, so it shouldn't get any issues. So at that time, given the basic design of the directory structure is present on all the subvolumes, you need to heal back that directory. So that's where the healing comes into picture, and I think the NFS ran into this, especially the NFS v3, which is Gluster NFS server, has lots of its issues. So you add a brick and everything is broken. You do a git clone after an add brick, it seems broken, it won't work. So the current status, we have some patches from in the last year that's been fixed, and basically the credit goes to the tiering team. So basically they were working on, they faced these issues, and so it's to the tiering team this fix got in basically. So the other problem is one of the main complaints about DHT is basically read is slow. As you keep adding more bricks, you would find ls becoming slow, find becoming slow, and any operation which is basically involves this traversal of this directory structure like tarring, untarring. So all this becomes slower. One of the reasons for that is basically you are replicating all the directories. There is a lot of redundancy in terms of directory. Assume a setup where you have lots of directories, and all these directories are replicated on all the subvolumes, and while reading you have to read from all the subvolumes. That's another requirement from DHT. Basically a directory is spread on multiple subvolumes. In order to read a directory completely, we have to read the directory on multiple subvolumes basically. So reader has to read dot of entries, and this chatter goes around the network basically. So it has to traverse the network, hit the POSIX. So even reading from backend file system, a large directory itself is a pain, and now add to it more the complexity of sending all the data over the networks, replying, sending more requests, more replies. So that's where I think one of the prime suspects for read performance. So actually there have been kind of hacky ways to work around it. Basically there is an option in DHT called read optimize. So if you set that option, what it does is it for the directories which corresponds to directories. So the directories which are correspond to directories are read from the first subvolume. So in that case, we have observed things are not as bad as they are when you're reading from the directories from all the subvolumes. So that kind of gives an indication that the redundancy of reading all the duplicate directories is causing issues. So the next major complaint is basically the directory operations have to visit all nodes, and it has some consequences. The first consequence is basically for RMDIR and RenameDIR to succeed, you have to have all the subvolumes up. Even if one subvolume is down, your directory operation like RMDIR or RenameDIR, basically they'll say E not con. So that's a problem basically. So you say DHT has no single point of failure, and one subvolume fails, and you are not able to perform any directory operation. Not all the directory operations, particularly rename and RMDIR. However, the saving grace is mkdir can complete with just one subvolume up, which is basically the hash subvolume. So that way, the directory operation having to visit all the subvolume is not bad, at least for some operations like mkdir. And the other thing is these operations are basically two-stage operation. Basically, you do one operation on the hash subvolume, and then you do the operations on the rest of the subvolume. So basically, it's the total cost is basically 2 network hops basically, and the slowest subvolume, which the cost is basically the time it takes to reach the slowest subvolume. Yeah. So I remember. So basically, the way we used to market Gluster or DHT was basically lack of MDS. So though it is good in aspects like large directories or shared file operations across distributing the file operations across multiple subvolumes, it makes things for a developer too basically. So that's what I am trying to say in this slide. So there are metadata. Basically, these are the issues we are facing here is maintaining the metadata for a directory. So the metadata can be permissions, or the logs we acquire, or the applications acquire, the POSIX logs, file logs, and all those things. So now, since we say all subvolumes are equal, basically we are kind of forced to provide the replication logic. So the replication tries to, you know how complex it is to maintain the mirroring for a file data for a replication. So similar problems we face to maintain the consistency and mirroring the metadata for a directory here. So one of the easy ways is basically we can choose an MDS model basically and use hash subvolume. The hash subvolume can be an MDS model, though it's not a well publicized MDS. Basically, it can differ for each directory. So each directory can have a different MDS, and we are going to do operations like setxatter or reading the permissions only from that particular subvolume, and if it is down, basically those operations can't succeed. So that's the problem with going with the MDS approach for permissions and other metadata. But the problem is the other approach of mirroring on all the subvolumes and hence providing the HA is kind of equally difficult actually. Yeah, so the other point is basically the directory is spread on all subvolumes. So the corollary of this is basically for a reader to complete, it has to visit all the subvolumes, and only then you can say that the direct reading is complete. Now, though it is not such a problem for directories containing lots of directories, basically large directories, the problem can be easily seen for small directories. To give a more standing out example, let's say an empty directory on a big cluster. Let's say you have hundreds of subvolumes for DHT, and you try to do an LS in an empty directory. And the current model is that basically it serially visits all the 100 subvolumes, and then only then the reader can complete. So and this makes it difficult for use cases like home directory users where you don't expect too much of files in a home directory. Yeah, so that's one of the major problem with the DHT one. So and the corollary is basically when I saw this problem, I was asking myself why can't we parallelize the reader? Basically, I can wind down the reader to all the subvolumes, and basically that makes the reader operation O of 1 actually, irrespective of the size of the directory. But the problem with that approach is basically the support for the rewinder. So rewinder, the support of rewinder requires that we maintain the offset guarantees. So basically you need to, if you rewind to a particular offset and start reading the directory again, you shouldn't miss out any entries what you had given earlier. So basically the ordering you have to maintain. So because of that's the reason why it was serialized actually, to make the reader simpler and maintaining the offset. And I'm not sure, basically even the backend file system also, they say that I have read on online forums saying that the rewinder requirement is also basically making their directory implementation complex actually. So the people from who have experience in the backend file system might add to it actually. Yeah, so I made a point that though it may not be a problem with the larger directories, it's a problem for small empty directories. The reason is that we have a translator called reader-ahead. So the reader-ahead, it kind of tries to hide the latency of a reader. Basically, it prefetches the directory entries, and so that by the time application requires for the directory entries, they are ready in the cache. But the problem, if it's a huge directory, even in an MDS model where the entire directory is stored in one particular subvolume, you have to sending the reader calls on it, and it works out. But the problem here is when you switch over from one subvolume to another subvolume. Basically, let's consider the case of an empty directory. Let's take a case of 3 brick scenario, B1, B2 and B3. So to figure out the brick 1 is empty, first you have to send out one reader, because you don't know whether the directory is empty before you start a reader. So you send a reader there, and only when it returns EOF, basically you send a reader to B2 and then to B3. So basically there is a serialization when switching from one subvolume to other subvolume. So that serialization is what costing us the scalability bottleneck here. Yeah, so this is another one of the commonly faced user issues. Stale in-memory directory layout. So if you are, as you might be aware, DHT has as a design of maintaining independent layout for each directory. So which means that layout changes it can change for any reasons, being an add brick or a remove brick, or at the time of healing something bad happened, and at the time of directory creation the setx setter failed. Basically your layout was not set properly. So at the time of the access it tries to heal it, and when it tries to heal, the thing is the healer, there is no guarantee that it will come back with the same intended layout as the previous healer has set. So which means that the layouts can change. And one very obvious case is an add brick, where the layout can change. After an add brick, obviously the distribution layout won't be the same, because you also have to accommodate an added brick or a removed brick. So what it means is, to make the operations faster, DHT caches the layout. Basically, you cannot, when a file creation operation comes, you cannot go ahead and read it from the backend always, the layout. So it caches it in the memory, and as with caching, we have cache coherency issues. So this is what the stale in-memory layout, directory layouts. So the 2 points speaks about what are the cases where we run into stale layouts. One is basically healing by multiple clients. The other one was basically when you are trying to run a fixed layout. The initial version was a case where every rebalance process went ahead and set its own layout without even checking whether the layout needs healing or the layout needs fixing. So there are two aspects here, healing and fixing. The healing means basically you are not changing the spread count. If you have a spread count of 3, the 3 subvolumes, the spread count remains the same. However, the fixing of the layout means it tries to pull the layout on all the subvolumes basically. So the fixing is only done by the rebalance process. The healing is done by even the client process. So this problem has been partly fixed now. We don't run into the stale layouts as frequently as we used to run, but we have not solved all the cases. So the stale layouts, there are 2 possible solutions which have been proposed, and one have been kind of partially been worked on. The first one is kind of borrowed from DHT2 basically. It says a single global layout for all the directories. So in that case, you may not even necessary to store the layout on the back end. So since you are not storing and you are always deriving a layout, there is no question of the staleness here. The second one is what we have partially attempted and is kind of present in the code, though it doesn't cover all the file ops path like create, link or rename or this thing. So it covers only the mkdir path. I don't think it's necessary to go into the details of it, but yeah, so those are the 2 broader approaches we are trying to work on. The single global layout is in the state of POC actually, so probably we might have something in the near future. Yeah, so the other common scenario we normally face is if you open the Bugzilla, you can find quite a few bugs on this particular issue, which is basically a brick fill scenario. So the whole purpose of DHT is basically to add more capacity. So what happens when a single brick is full? However, the data is the space is available on rest of the subvolumes. So that's the case this point speaks about. So though we we can create link to files. Link to files are basically the pointers saying that where you actually can find the data of the file. So though we have link to files which can point to the other nodes, it might so happen that the brick where your file hashes to, it doesn't have enough space even to create those link to files. It might have run out of inodes. It might have no space to store the extended attributes, to store the metadata of link to, as to say where exactly to store the file. So that has resulted in kind of weird bugs where you see two listing entries for a file and the 0-byte files and all those things. So we kind of evolved. There's an option called min-free disk, basically which prevents new files getting created on a particular subvolume once it has when the space usage has crossed a particular threshold. That kind of avoids this problem to a certain extent, but it doesn't make the problem go away. The reason is that even though you are not creating any new files in the same subvolumes, the files which are already present, they can grow, and they can grow and consume all the space, and you may not be left with any space to create these link to files and all those things. One of the couple of solutions which I could think of for this problem is basically sharding. So the sharding, with sharding, your file size is the maximum limit of a file size is basically a shard size, and beyond that it cannot grow. So and with that and probably a kind of backend calculation about existing number of files and this thing, you can say that min-free disk is you can arrive at a meaningful min-free disk so that your existing data won't grow and cross the min-free disk. So the min-free disk is a buffer which is used to store, which makes sure that DHT will be able to store all this internal metadata like link to files and all those things. The other option is maybe on the file migration of the file during writes. Basically, when you in the write CBK or in the write, you see that allowing this write causes the this particular subvolume to exceed the threshold of min-free disk, and you can trigger on-the-fly migration, but we are no way closer to it. The on-the-fly migration is a complex actually, so we haven't really attempted it. So that's just an idea. Yeah. So the other pain point is basically you run into this while running the rebalance. I think Tier ran into it very much because initially they were using the model of directory, no MDS kind of model. So what happens is basically it is a corollary of serially visiting the subvolumes during the read. Let's say in the first iteration of a read, you visit subvolume 1 and the file was not present on the subvolume 1, and by the time you reach to the subvolume where the file is actually present, the file has moved back to the first brick, which the reader has already completed. So basically you might end up seeing no file at all in a reader listing while the rebalance is happening, or you might end up seeing duplicate entries. Basically you see the file in multiple places. Then the another major pain point is basically the rebalance speed. So though the rebalance speed by itself might not matter to the application, there are cases where makes that the users need to be aware of or might be worried about how long this rebalance might take for completion. So one is basically kind of everyone needs an estimation, like how long it might take for the rebalance to complete. That's the first thing. The second thing is lack of granularity. You cannot pause a rebalance, so it's monolithic. So you cannot start the rebalance while in the middle of while it has rebalanced few directories and then resume from it. So that's a lack of granularity. You cannot rebalance one particular directory or two directories or resume from rebalance which is stopped in the middle. So the other problem is basically missing directories in ready listing doing rebalance. So what that means is going back to the design of the DHT, because of the HA guarantees, your directory should always be listed. If it's a directory, it should be listed when you do a listing of its parent directory. Because if you miss out a listing of a directory, basically the entire subtree of the directory is lost. You will not be able to access the data. So though let's say some subvolumes are down, but the directory, since it is spread on all the subvolumes, it might contain data on the up subvolumes. So the corollary is that you always need to try to provide a case where your directories are always listed. Now, but the problem with this is the another point is basically the directory entry for a directory is present on all the subvolumes. However, the application is aware of only one directory. It doesn't want to see multiple duplicate listing for the directory. So what do we do? So we have to filter. Basically, we have to take the directory entry from one subvolume and ignore the entries from rest of the subvolumes. And the filtering logic, there should be some logic. We took the logic of, let's take the entry from the hash subvolume. Now the hash subvolume is a function of the layout, and the layout can change during rebalance. And when you add a brick, basically an empty brick, the directory obviously won't be present in the new brick because it's a new brick. And to creation of the directory structure on the new brick, it takes some time. Basically, the rebalance has to crawl to that directory, basically the entire subtree, and access that directory over the mount point. Only then it gets healed. Basically, the point I'm trying to convey here is there is a window of time where your directory need not be present on the hash subvolume, and that scenario is basically an add brick scenario, and the newly added brick is your hash subvolume. So you fix the layout of the parent, and when you include the newly added brick into your layout, but by the time till the time you heal the directory on the newly added brick, your directory might not be visible, and hence all the subtree is not visible. And it might seem like a trivial problem, but we have a use case where a user was not able to see a directory for 2 days actually because of because they had more data, and the healing is tied up with the data migration, and they kind of go serialized. So it all made things complicated, and directory was not being listed for 2 days. So that's a bad thing. Yeah, so that's it for the rebalance speed, I think. Yeah, so these are some of the problems I have normally seen in the BZs, along with the interaction with other team members and customer cases and all those things. But that points to the question, like, are there any advantages with this design? Basically, do we see, even with all this complexity, does it has anything to offer? First point may not be a really solid point given that we have seen so many bugs and other things, but still it kind of says that there are no, the unknowns are less. I wouldn't say there are no unknowns, but the unknowns are less. So the other main point is basically the distributed workload for directory ops for files under read. So basically this all goes into supporting large directories. And let's say there's a file. It's not just the read and write workload that is spread across the subvolumes. It's also the read workload is spread. The lookup operation of resolving a path into inode, that is also distributed. And the other file operations, directory operations related to file like rename. So those things are also spread out. They all don't go into one particular subvolume. Yeah. So the other point is no single point of failure. Yeah. So the no single point of failure point applies only if you maintain the guarantee that a directory is listed always. Because if a directory is not listed for some reason, basically you're losing the entire subtree of data. There are some bugs where you might see the directory not listed, but I think there's nothing in the design itself which prevents from achieving this goal actually. Yeah, so the other point is basically it can support really large directories because the directory is sharded across multiple subvolumes. The next point is because it's a kind of consequence of independent layouts. If you have a scenario where some subvolumes in your cluster is down for a long period of time and you are creating directories, the independent layouts make sure that the files won't go into those subvolumes which are down. Basically, the directory is contained into those subvolumes which have been up at the time of the directory creation. But that doesn't mean that you would never see errors while accessing the files, like errors like inode.conf, because that's only during the directory creation. The subvolumes can go down after directory creation, and in that time, when you try to access files, you might get an inode.conf. Yeah, the other thing is basically since the directory structure is present on all the subvolumes, the abstraction from the backend file system is not complex. You can just mount a subvolume as an independent subvolume and access the data without having to do too much of work to overcome that abstraction. Yeah, so that's it, I think. Any questions?
Lots. 3 questions.
Yeah. Yeah, done.
That was a good presentation. There was a discussion that was on Gluster Dev that you initiated a couple of weeks ago regarding ordering from the standpoint of the user. Can you summarize the results of that discussion? What was the outcome, the answer?
The ordering of what?
Ordering of operations from the standpoint of the user. So if you send 2 file operations, they're ordered somehow.
That was related to write behind issue. Is that thing?
Can you describe?
Okay, so it's not. Yeah, so birds of feather session. I think it's not really related to DHT. It's the ordering is mostly with the write behind translator, because like it tries to cache the writes, and because of that, once you have responded back to the application might do more write operations, and those ordering might go bad, I think. So we can probably speak that.
Are you going to have a birds of feather on right behind in particular?
Yeah.
Great.
So one of the complaints that we actually hear from users is adding extra subvolumes. Like if you have a 4+2 EC volume, and if they have to do an Android, they have to buy 6 more servers. So which they find it like really costly, and instead they would like to add just one server with more disks, and they expect cluster distribution logic to take care of it, like how it has to place the files, etc. So do you have any ideas about how to do that in DHT?
Short answer is we don't have any outright ideas to solve that problem as of now. But as we are discussing from last few days or sometime, so basically it requires more close coupling with replication logic, distribution logic, and all those things. So given the complexity it is, it's not to be in a short term, I think. So that's the feeling I have about it.
So one comment, could you repeat the questions? I think this for the recording.
Okay, okay. So the question was, so basically, take a simple case of AFR. So the current logic of addition of bricks requires you add bricks in the multiples of the whatever the replica count. So, but the user always don't like, they might buy one node and they want to add it in terms of one brick actually. So, that requires more efficient utilization of the bricks, flexible coupling of bricks for the files. For example, a file 1 can be replicated in B1, B2, B3. A file 2 can be replicated in B2, B3, B4. So basically, kind of a round robin algorithm or whatever algorithm we choose to. But the current distribution logic is kind of, if a file is B1, B2, B3 are always replica pairs. They are not coupled with any other replica pairs. The replica pairs are exclusive, so they won't overlap. So that was the problem. So his question was, are there, how are we going to solve it, or are there any plans to solve it? So the initial thoughts revealed to that it requires more tightly coupled distribution logic and replication logic, or but we are not there yet as of now.
One more. Last question.
Is the support for the reminder the only reason why parallel reader is not sent?
That's the primary reason. So
Repeat the question for the recording.
Sorry. So the question was, is the support for reminder the primary reason for not doing read-dir parallelly on all the subvolumes? The answer is the primary reason, yes. That's a thing, because we need ordering and we need predictability in the offsets. Because if you read-dir parallelly, you might get the entries mixed up in different orders, and the next read-dir iteration you might not get in the same order. But yesterday, as we were discussing with Xavi, so and Pandit and Xavi also pointed out that even with parallel read-dir, you may not solve all the problems, because like there's still the cost of associated of sending so many number of parallel requests over the network and processing their replies would still remain. So you are basically consuming more threads, more CPU, more network for sending out so many requests. So that's a secondary problem, I think.
All right. Thank you very much.
Thanks, everyone.
All right, quick coffee break. We're running mostly on time-ish, so, talk amongst yourselves, be shade out.
There you go. Thank you.
Does this laptop have LibreOffice?
I believe so, yes. Amy,
And
put them all here. Yeah, you're going to need that. And you should probably, actually, before you do that, can you take your lanyard off?
Oh, yeah, sure.
That way it won't bang into it. Oh, yeah. To be honest with you, I think I'm just going to...
I'm very bad with mine. So
You're fine. I'll put it there, a little closer. There's also a mic here that's for the camera to just try not to bang it. You don't have to mess with it. Yeah.
Let's see, when are you?
You can put that in your pocket if you want to move around. Yeah, over there. And then, as you saw,
Let Cheyenne actually
repeat if you get any questions, repeat them, because then the camera can pick it up. You're good.
we could do so. I mean, like, maybe we could, no, maybe I could look at the app. Basically, like, we need to- Okay, I'll let him know. Okay. Yeah, of course, yeah.